Hi students, this is the fifth module on discrete Fourier series or discrete Fourier transform. In this video, what we would take a look at is, suppose you have a finite length discrete signal, discrete time signal. Okay, you take DTFT of it, and then you sample the DTFT, and for that you can the samples of the DTFT you consider as your x tilde of k, means the DFS. Okay, and you take inverse DFS of it, and then what we are going to study is how your original x of n is related to this x tilde of n. That's the objective of this module. So let's go ahead. Hope you are able to see this. Hope the screen is visible. Okay. Yeah, let me go. So what assume that you have some signal here. Okay, any signal. Let's call it as some x of n. Okay, so let's say 0, 1, 2 and so on up to, let's call it as n prime minus 1. So the length of that, this is your n. I have a signal which I refer to as x of n. So I have a finite duration signal whose length of that signal is n prime, is the length of my signal. Given that signal, how could I, for example, I'm interested in the DTFT of a signal given a Z transform. For example, how do I write DTFT? X of e power j omega is equal to, if you are given the Z transform, the frequency response on the unit circle of your Z transform is going to give you the DTFT of that particular signal, right? And then next step would be take on this Z transform. So let me write out, for example, here the real axis, imaginary axis, this is your Z plane, and this is your unit circle, right? And this would, the unit circle, if this, the whole thing is x of z, this would give you x of e power j omega. What is it that we are interested now is to take samples on this unit circle, and that too we are interested in taking samples at uniform distance, right? And that's what we call it as the DFS of a particular signal. So let me rewrite it here again. We know that x of e power j omega is x of z computed at z equal to e power j omega. Now I want to take samples of this, right? And that, let me call it as x tilde of k. Notice here, after one period of 2 pi is over, they get repeated. So this being omega being the angle, x tilde of k. How am I going to get that? For x of e power j omega, I would like to take the samples at, so this relation we worked out earlier also, uniformly spaced samples, right? So overall angle is 2 pi, n samples I want to take. So omega equal to 2 pi by n into k will give me uniformly spaced samples, where between any two consecutive samples the distance is equal to 2 pi by n, and thereby giving you n samples, is it not? Now if I write x tilde of k, can I express that now in terms of x of z? Why not? X tilde of k is equal to your omega should be this, right? So on x of e power j omega, if I take z equal to e power j times omega is equal to 2 pi by n times k. Let me also emphasize here, in order to construct x tilde of k, n samples are taken. N samples are taken for constructing x tilde of k. In other words, the periodicity of x tilde of k is n. Now what we would like to investigate here is, I'm just phrasing whatever we have done so far. So let x of n be a finite duration, discrete time signal, discrete time signal of length n prime. Okay, that's what is given. Now so for a suppose now, let the DTFT of x of n be sampled at with a spacing of with a spacing of 2 pi by n, right? That implies resulting in how many samples? N samples. Okay, now that's what would give you now x tilde of k, correct? And then from that you compute inverse DFS of this, would give you x tilde of n. Now the question that we are going to investigate is, how are x tilde of n and x of n are related. Okay, that's the question of our interest for us, right? This also under 3 cases. For example, the number of samples, uniform samples you are taking could be greater than n prime. Okay, then how are they related? You might be taking the same samples, then how are they related? And suppose if I am taking less number of samples, how are they related? So this is what we would like to study in this video lecture. Right, now what do I have now? There is x of n, for which I am calculating x of e power j omega. How do I get that? Given x of n, your x of e power j omega is equal to n varying from minus infinity to plus infinity, x of n into multiplied with e power minus j omega n. Now what am I doing? From this I am getting x tilde of k. How do I get that? You take samples of it at, by the way, this got x of e power j omega is n equal to minus infinity to plus n. I take this samples of it at an intervals of 2 pi by n times k, right? That would give me x tilde of k. What is that value? X tilde of k equal to, you simply substitute there in place of omega that particular value. That would give us, let me use another variable here, let's say m here. Let me use here m equal to minus infinity to plus infinity. If you want, you write the x of e power j omega is also that. Okay, x of m into e power minus j, my omega is equal to 2 pi by n times k times m. This is the x tilde of k. Given x tilde of k, how do I get x tilde of n? To do that, your x tilde of n expression, the synthesis equation that we are talking about, is equivalent to 1 by n summation over k varying from minus infinity to plus infinity x tilde of k into e power j times 2 pi by n times k times n, right? Now let's substitute here x tilde of m here. Let's substitute this in this equation. That's how we are getting x tilde of k. So that would give us x tilde of n is equal to 1 by n times k varying from minus infinity. Wait a minute, I made a mistake. K varying from 0 to n minus 1 here. Okay, that was a mistake. This is a periodic signal, you do it for that, n minus 1. Okay, so here also let me correct that out. This is varying from 0 to n minus 1, and in that x tilde of k, let me substitute that m varying from minus infinity to plus infinity, x of m times e power minus j times 2 pi by capital N times km, that is my x tilde of k. That anyway is multiplied with e power j times 2 pi. Wait a minute, something had happened, it got closed. Let's write again, opened it back. So erase this, okay, and then take that k varying from 0 to n minus 1. The x tilde of k value is m varying from minus infinity to plus infinity, x of m into e power minus j 2 pi by n times km. That's your x tilde of k, anyway getting multiplied with e power j 2 pi by n kn. As we do all the time, the moment you see two summations, interchange and see what is going to happen. We'll do the same thing here. Okay, that implies, so what is it that you are going to get? This is equivalent to 1 by n. I would write outside m varying from minus infinity to plus infinity. What are the terms that are just dependent on m? This one. So let me keep it, bring it out. All the rest have something to do with both k and m, right? So let me keep them. Yeah, let me also take this 1 by n inside for a reason, should be clear very soon to you. X of m into 1 by n times summation, I write here k equal to 0 to n minus 1, okay, and e power j times, let me combine those two complex exponentials, j times 2 pi by n into k times n minus m. This is where we arrived. Okay, do you remember this guy, seeing him sometime earlier? If not, you go to the second module of your DFS, where we started with x tilde of n as the impulse train. We tried to compute the DFS, we got as 1, that you have taken, and then for given that x tilde of k, if you substitute it there, and then you would realize that this is nothing but equivalent to an impulse train having value at k equal to 0 as or impulse train with n equal to 0 it has 1, and the rest n minus 1 values being 0. Okay, and that being periodic, you could add there plus or minus Rn. If you don't remember this result, please go to the second video of on DFS. Okay, so I am using that result here. This would give me m varying from minus infinity to plus infinity, x of m into, you get, this is nothing but the this summation would be equivalent to an impulse train with a periodicity of capital N. So that impulse train, So I vary from minus infinity to plus infinity. That impulse train has a value when n minus m equal to 0, that has one value, and then it has a periodicity for varying values of r. For every n minus 1 values you have one impulse. So this is what you would be getting. Okay. So again, does this expression ring something in your brain? X of n into n minus m minus rn. Okay, if this is not very clear to you, think of it. Let's write this as slightly rephrased one. I could have written it as n minus rn minus m. Okay, that's nothing but a linear convolution of x of m with this, is it not? So this is nothing but, I could write this expression as this x of n linearly convolved with an impulse train or varying from minus infinity to plus infinity delta of n minus r times n. A very important result for understanding the DTFT later. So this is what you got for x tilde of n expressed in terms of the original x of n when you have taken DTFT of x of n and took uniform samples of it with a sampling rate of capital N. Okay. Yeah, these two simplification steps should be clear to you. The first one is the result we derived in the second DFS lecture. Third one is convolution of x of n with y of n is x of k into y of n minus k, right? So that's exactly your small n here is n minus rn. So that's all. Hope this result you are able to see that clearly. What is the implication of it? So I repeat here again what we have done. We started with a discrete time. So let me go again perhaps to some diagrammatical representation of these things. Hopefully that should make things simpler for you. Wait a minute. Let me open the corresponding some inferences of that. Okay, this is a good example of that. Okay, let me start here. As far as this presentation is concerned, you created x tilde of k. Okay, this is the DFS of a function by taking uniform samples on the complex exponential plane. That's how you started with. Then what you got here is for this x tilde of k, if you have computed the inverse DFS of it, okay, that would give you x tilde of n. What we found out is this convolution with an impulse train. I'm sure you all remember it from sampling. This will place copies of it, right, at n equal to all integer multiples of capital N. This is going to place copies. So by this time, so we again, I again remind you of the question with which we started with. Suppose your signal x of n is of length n prime is the length of it, of your signal. Now you have taken capital N samples at uniform distance on this unit circle. Okay, so then what's the implication of that is what we are going to study here. You see this now. Let's say this is your signal of finite, this is your x of n of finite length 9, right? And then what is going to happen? How are you getting x tilde of n? Now assume you have taken 12 uniform samples of it. So delta impulse train would keep the next copy at 12. So this is the copy, next copy placed. Similarly on both sides the copies are placed. Okay, so this should be the another copy that is placed, right? That's your x tilde of n. So if you look at within the range of this 0 to n being 9, if you look at from 0 to 8, the signal would remain same here as long as your n prime is greater than n, capital N is greater than, from here you could see, as long as your capital N is greater than or equal to n prime, within the range of 0 to n prime minus 1, your signal would remain intact. Now let's see the another case where suppose my n prime is 9 but I am taking only 7 samples of it. See what's going to happen. From the expression of that impulse time, this is the first copy is shown in red. The second copy being this n being 7, delta of, recollect that, delta of n minus r n for varying values of r from minus infinity to plus infinity, you are keeping it. So the next copy would be placed here at n being 7, at 7 itself the copy is placed. So what's happening now? These two values are getting corrupted, or compared, by corruption we mean, are they same as the values in x of n? If not, we are referring it as corruption, the value getting corrupted. And another copy is placed at, for example, where is the another copy placed at the periodic copy is placed on the negative side also, that again corrupting two values here. So this is what is happening if your n, the number of samples you are taking, is less than the n prime. Okay, hope these things are clear. So this is nothing but, this is referred to as aliasing is happening, very similar to the aliasing you have seen in the frequency domain when you are not taking enough samples. Earlier what happened, if you are not taking enough samples in the time domain, you had an aliasing in the frequency domain. Now pay attention here, we are taking samples in the frequency domain, n being smaller is, in other words, not taking enough samples. You now can observe aliasing in the time domain when you assume that you are just taking one period of the signal and taking a look at what's happening here. That's the time domain aliasing. Okay, hope you, this is the time you could see the similarities again between the time domain aliasing and the frequency domain aliasing, and when you could avoid it. Assume that at the end of the day, after the whole process, you could think of it this way. You have a signal, you discrete time signal of finite length of n prime, you computed its DTFT. How many samples should I take to get back my n? Okay, if you just are taking samples, inverse DTFT is not going to work. So what you could do is you take samples, right? Anyway DTFT is periodic, so your samples also will be periodic. So what you have there, here, there, you could think of it as x tilde of k. From that you compute inverse DFS. From that would give you x tilde of n, and you simply take one period of this x tilde of n. Okay, and that you compare with x of n and how they are. So what is happening here is, as long as you are in order to construct x tilde of k, if you are taking samples, be uniform samples of n, as long as it's greater than or equal to n prime being the length, non-zero length of x tilde of n, then you are able to perfectly get back with just, if you have n prime, you want to keep things minimum, just take n primes samples from DTFT, that you treat it as DFS, that you take inverse DFS of it, you take one period of it, that's going to give you x tilde of n. So to come back there, let's recollect what has happened in the sampling, in the frequency, when you are there is a continuous time signal, you are taking samples of it, or you already have a discrete time signal, you are downsampling it. There, to reconstruct back the original one, what should have happened when you are doing it? First of all, there were band limit, as long as the signal is band limited, right, and your number of samples rate is greater than or equal to 2 times that maximum frequency that you have it, you are able to perfectly reconstruct the signal. So your signal should be band limited there, the first condition, to avoid frequency domain aliasing. And your sampling rate in the time domain is high enough, okay, that given by this. Same thing now, for the first time you are getting a time domain aliasing. Now time domain aliasing would come when you are taking samples in the frequency domain, and while you are taking it, for that, just like your signal should be band limited, this x tilde of n should have a finite known length. So the sequence, and then only you could tell here how many samples you should take. The number of samples should be greater than or equal to the length of the signal. The sequence has to be finite. Second condition is that the sampling interval in frequency domain is small enough. It is small enough. In other words, taking enough number of samples. In other words, increasing the high value of n. So this n should be high. That is how you could avoid the sampling. So this is the relationship. Okay. With this, we are done with this topic of. Let me come back here. So the topic of sampling the Fourier transform. Okay, and then 1 minute. Just let me keep it intact. Okay. So yeah, in this, to summarize, in this video module, we have discussed about, you have a discrete time signal of finite length. From that, you compute the DTFT of it. If the length of the signal is n prime, as long as you sample that with a value more than or equal to n prime, and consider that as DFS of a particular function, and compute that particular function, let's say call it as x tilde of n. From that you could get back x of n as long as your n prime, by just taking one period of it, as long as your sampling rate n, capital N, is greater than or equal to the length of the signal. Okay, that's all for this video lecture. We'll discuss more in the upcoming videos. Okay, thanks for watching, and see you in the next lecture. Yeah, bye, take care.